Hey everybody, it's Mrs. Dinkelman, and we're in Unit 13, and now that we've done the basics of polar equations, we're going to get to the calculus part of it. So we're going to start with the derivative, and what I hope that you'll see is that the derivative here is just a lot like it was in parametric. And so instead of being like a dy dt over dx dt, it's just dy d theta over dx d theta. Now that's just what I do every time. But some people will memorize or they will derive what's happening on the right-hand side, which is this r cosine theta plus dr d theta sine theta. Now, maybe it's not so bad, but I'm just afraid I would get mixed up where the sines go and cosines and the negatives and all the positive. So it does take me perhaps a little bit longer to figure out what dy dx is because I don't have that stuff on the right memorized, but I'm kind of willing to sacrifice that because I know I'll get the right answer easily. So let me talk you through what I mean by how I calculate it. So I have to remind myself that r, or y is equal to r sine theta. So here in example 1, we're talking about y equals, instead of an r here, 3 plus 8 sine theta times sine theta. Now I have to decide if it's worth distributing. I'm going to say no because I don't have a sine squared and I have to do chain rule. I'm just going to go ahead and go with product rule when I'm finding dy dx. And then x is r cosine theta. So then in this case, our r is 3 plus 8 sine theta, and then cosine theta. Okay, so let's figure out what dy dx is here then. Dy dx is going to be, so the derivative of y, so I'm looking at this one, I'm going to have to do product rule. So first times the derivative of the second plus second times the derivative of the first. Okay, and then dx d theta, so now I'm taking the derivative of that one. So first times the derivative of the second, make sure I get that negative really in there, that's times that, plus second times the derivative of the first. Okay, so maybe now you can kind of see the comparison between what's going on here. Like I see this negative sign right here that was there, okay? I see the r value that was there. I see the cosine, I see the r. So you can kind of see why all of these pop up. It's just for me, it's not that bad to try to figure out what's happening there. Okay, so now I guess we could simplify, but I'm just going to go ahead and try to figure out what's happening at theta equals 6. I should leave myself a little bit more space there. Okay, so we're going to have, and again, we might have a calculator for this one, but I'm going to go ahead and pretend I don't. We'll see how far I can get. So we have 3 plus 8 sine of, so pi over 6, that's going to have a smaller y coordinate than it will an x coordinate. So 1/2 is going to be the smaller than root 3 over 2. That's what's going to go here on the outside, plus, so 1/2 times 8 root 3 over 2, and then 3 plus 8 times 1/2 times negative 1/2, and then root 3 over 2 times 8 times root 3 over 2. All right, we'll see how far we can get there. So this is going to be 3 plus 4, that's going to be 7 root 3 over 2. Just by the way, remember on the AP exam, if you get this far where you've plugged things in, technically you can leave that on a free response. Okay, so this one is going to be 8 over 4, so 2 root 3. And then let's see here, we're going to have negative 7/2. And then let's see, that's going to be a 2 times 3, so 6. I'm just going to leave it like that, I guess. If we really wanted to find out from there, we definitely could, but it's just going to take up time on the video. So arc length on this one, I would really want this one to work because then it's just like parametric. But it turns out that a lot of times they tend to use this formula at the setup, and then this just gets really big. Because imagine, again, if we're doing the same problem from up here, imagine I have to take the derivative of y, which is really this thing that's on the top, and the derivative of the x, which is the thing on the bottom. And then I have to square both of those and put them in this formula, and then square root them, and then take the antiderivative, which is possible. It's just sometimes it turns out to be just a lot to try to simplify and figure out what's going on. So instead, if you think about r squared plus drd theta squared. That's a lot better formula to use. And once you have that memorized, it's just a really simple thing like we've been doing, a little bit more complicated as far as what the integrals look like than some of the other ones. But so we're just going to go r squared, so -4 sine theta squared, and then the derivative of that. So that's going to be -4 cosine theta. And then a lot of times these will simplify, because right here what we have, just by the way, is 16 sine squared theta plus 16 cosine squared theta. And if you remember, if I wish I was sine squared and you were cosine squared, because together we would be 1. So that's actually going to be a really simple one to figure out. I'm going to go ahead and keep going with it. So I think what we have in here is, and I'm going to just write a couple more things here so you can see what I mean. Okay, so remember this is 1, and so I really just have the integral of 40 theta. And so that's 4 theta from 0 to pi, so it's just 4 pi. Okay, and I think that's it in calculus. We're going to take the area as a separate section just because it's kind of something different to talk about. So go ahead and get going on this section, and then we have one more section, which is area.